there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 10, The Power of Algebra, Finding Pythagorean Triples. Okay, sounds like geometry to me. All right, anyhow, classwork opening exercise. Sam and Jill decided to explore a city. Both begin their walk from the same starting point. And then it says Sam went this far and that far. So let's do that. So I will use green for Sam. Sam walks 1 block north. So let's start him at the origin, of course, where he originated. That's why it's called the origin. That's where we start. Sam walks 1 block north. That would put him here at 0, 1. Then 1 block east, which would put him over here at 1, 1. Then 3 blocks north, 1, 2, 3. That puts him at the point 1, 4. And then 3 blocks west, 1, 2, 3. So there he is at the point -2, 4. Okay. Jill walks 4 blocks south. So she's starting at the same point as he did. Went 4 blocks south. That's the point 0, -4. Then 1 block west. Whoops, west is this way. So now we're at -1, -4. 1 block north. So she started here. She went 4 blocks south, then 1 block west, then 1 block north to the point -1, -3. And then finally 4 blocks east. 1, 2, 3, 4. So she ended up at the point 3, -3. Okay. If all city blocks are the same length, who's the furthest distance from the starting point? Well, to find a distance diagonally on a grid, we need to do either the distance formula or the Pythagorean theorem, which basically is the same thing. So I'm going to show it. I'm going to draw a triangle. So let's just do this and let's use green for him. So he started at the origin. So the most direct is to go straight up 4 and left 2 to get to the point -2, 4. And here is the right triangle. Right angle right here. Here's the right triangle. So if this is a side and that's a leg, I should say this is a leg and this is a leg, then this is the hypotenuse. By definition, the hypotenuse is the side opposite the 90-degree angle, and it's the longest side of the triangle. The Pythagorean theorem states that a squared plus b squared has to equal c squared. The distance from 0 to 4 is 4. The distance from 0 to -2 is 2. So a squared is 4 squared, b squared is 2 squared, and that has to equal c squared. 4 squared is 16, 2 squared is 4, that has to equal c squared. 16 plus 4 is 20, and that equals c squared. Find the c, we take the square root of both sides, and we end up with c equals the square root of 20. I will now do the same with her travels. Switch to red. So she ended up at the point 3, -3. So to get from the origin there, we have to go down 3 and right 3. And here is the distance she is from the starting point as the crow flies. So this distance here is 3. And this distance here is 3. So I want to find the opposite side. So then I write the formula again. A squared plus b squared equals c squared. A is 3. B is 3. And we need to find c squared. So 3 squared is 9. And 3 squared is 9. And they equal c squared. 9 plus 9 is 18, and that equals c squared. I have to take the square root of both sides, and therefore we get c equals the square root of 18. Okay, well, the square root of 20 is greater than the square root of 18. So Sam walked the furthest distance from the starting point. All right, example 2 says to prove that if x is greater than 1, then a triangle with these side lengths is a right triangle. Okay, so let me just isolate these with parentheses. Oops. There are our 3 side lengths. Which one is C? We need to know which one's the hypotenuse to set this up correctly. So if I just chose any value that's greater than 1, how about 2? And I plug it in here. 2 squared is 4. Minus 1 is 3. If x is 2, remember x is 2. 2 times 2 is 4. So this is definitely not C. This might be. We need to do this one now. Plug in 2 here. 2 squared is 4 plus 1 is 5. And we have a Pythagorean triple. Remember the definition of a Pythagorean triple. That leads me to discuss that. A Pythagorean triple is a triangle whose side lengths satisfy the Pythagorean theorem, and all 3 sides are integers. Can't have any irrational numbers or fractions. All right. So, for example, if this were side length 5 and this was side length 12, and this is A and this is B and this is C, then we'd say A squared plus B squared equals C squared. 5 squared plus 12 squared equals C squared. 25 plus 144 equals C squared. 169 is 25 plus 144. That equals C squared. Take the square root of both sides and we get C to equal 13. So I have side lengths 5, 12, 13. Since they're all integers, 5, 12, 13 is a Pythagorean triple. Okay? So that's a Pythagorean triple. So we have this triangle. Let's just get rid of this and bring in a diagram. So now I know that this is C. And naming these A or B, it doesn't matter which order we name them. It just matters which is C. So I'm going to bring in a triangle. We know that x squared plus 1 is C, which is my hypotenuse. So here's a diagram with these side lengths. Okay, let me get rid of this 3, 4, 5 stuff. That was just an example to find C. So here's our right triangle, knowing that I'm going to name this vertex A, this vertex C because it's opposite. And we usually name our triangles the sides, the lowercase letter opposite the uppercase letter for the vertex. So if this is C, this is side C. And if this is A, this is side A. All right. So with that being said, what are we trying to do here? So I'm going to bring in a statement. So here's a note. By the converse to the Pythagorean theorem, if a squared plus b squared equals c squared, then a triangle with side lengths a, b, and c is a right triangle with a right angle opposite the side length of c. We're given that the triangle exists with these side lengths, so we do not need to explicitly verify that the lengths are positive. Okay, distance cannot be negative. Therefore, we need only to check that for any x greater than 1, we have x squared minus 1 squared plus 2x squared equals x squared plus 1 squared. Okay, that's just the Pythagorean theorem from above. My x squared plus 1 squared is c, my x squared minus 1 squared is a, and my 2x is b. So it's a squared plus b squared equals c squared. All right, so we're going to take it from there. Okay, so proof. We are given a triangle with these 3 side lengths for some real number greater than 1. We need to show that the 3 lengths, 2x, x squared minus 1, and x squared plus 1, form a Pythagorean triple. So we first need to show that 2x squared is equal to this. Well, what are they saying here? Remember, x squared minus 1 that's a. 2x is b. And x squared plus 1 is c. So if I have a squared plus b squared equals c squared, and my 2x is equal to this, well, they're saying all they're doing is subtracting a squared to the other side. So they're saying b squared equals c squared minus a squared. So if this is b squared, then c squared, x squared plus 1 is c squared minus a squared, x squared minus 1. So all they're saying is b squared equals c squared minus a squared. That's the first thing we're showing. So I'm going to write that. B squared equals c squared minus a squared. Okay, it's still the Pythagorean theorem, it's just in a different form. It's isolating b. Okay, so with that being said, when we substitute in, we are going to get 2x squared, because that's our b, equals x squared plus 1 squared, because that's our a. My c, x squared plus 1 is c, minus my a, which is x squared minus 1 squared. So this is just b squared equals c squared minus a squared. Okay, so now I'm going to continue further, and let's just expand this up so that we're just focusing on this. Alrighty. Well, here is a perfect square, and here is a perfect square, and here's a minus. So remember from prior lessons that if we have x squared minus a squared, that is going to equal x plus a times x minus a. Hopefully you learned that and memorized that from the lesson summary and problem sets from the last problems, or the last exercise or lesson. So we have x squared minus a squared equals x plus a times x minus a. And that's what we're going to do next. So first of all, just to make things less confusing, if this is x squared minus a squared, then x is going to equal, in this format, x plus a, x minus a. X is going to equal x squared plus 1, and a is going to equal x squared minus 1. So we want x plus a times x minus a. So I'm just going to rewrite this now. Well, what is x? This is going to equal x, which is x squared plus 1. There's my x, plus a, which is x squared minus 1. There's x plus a, times x minus a. X squared plus 1 is my x, times x minus a. So this is x plus a, I need a minus, forgot my minus sign, minus a. Okay? So we have x squared plus 1 plus x squared minus 1. Times x squared plus 1 minus x squared minus 1. Okay, I'm just trying to be really careful here. Alrighty, so now we need to simplify this whole thing. So this is going to equal, and here's where it gets a little gnarly. I'm going to show all my work. So notice the parentheses here. This is one term, and this is another term that we're multiplying. We need to FOIL this, and I'm going to show all my work. So the first is going to be this times this. My first term is therefore going to be, we have to FOIL the first. X squared times x squared is x to the fourth. Outer is x squared times 1, which is x squared. Inner is 1 times x squared, which is x squared. And last is 1 times 1, which is 1. So my first gave me this. plus, now I need to do the outer. So I'm going to change to red now for outer. Outer is going to be this times this. And don't forget this negative sign. Think of this as minus x squared plus 1 with that negative sign distributed. Okay? So now I'm going to do the outer. X squared times a negative x squared is going to be negative x to the 4th. X squared times 1 is positive x squared. Inner would, or that's the outer. Inner would be 1 times negative x squared, which is minus x squared. And the last is 1 times 1, which is 1. Okay, hopefully you're still with me. And then I'm going to say plus. Switch to green. That was the outer. Now I need to do the inner. Inner will be this and this. X squared times x squared is x to the 4th. Okay. Outer, we did f first times first. First times outside. First times last is outer. Okay. X squared times 1, which is x squared. Inner is negative 1 times x squared, which is minus x squared, times last, which is negative 1 times a positive 1, which is negative 1. Alrighty, plus, and then I'll use purple for last. Last is this term times this term. X squared, and I'm looking up here now because I distributed my negative 1. X squared times a negative x squared is negative x to the 4th. X squared times 1 is x squared. Negative 1 times a negative x squared is x squared. And negative 1 times 1 is minus 1. Whew. Look at that, will you? It's okay. We're adding all of these up now. So x to the 4th minus x to the 4th cancels. X to the 4th minus x to the 4th cancels. This is going to become 2x squared. I'm combining these like terms right here. These like terms are opposites. They cancel. These are like terms. They're opposites. They cancel. These are like terms. They combine to give us 2x squared. So look at all this stuff that's canceled. Now I have a plus 1 and a plus 1, which is 2, minus 1, which is back to 1, and minus 1, which is 0. So all these constants canceled, and all the x to the 4th canceled, and many of the x squareds canceled, leaving us with 2x squareds. Now remember what we're trying to prove here. We're trying to prove that 2x quantity squared equals this. So now I'm going to say, well, that's 2x quantity squared. And I have a 2x squared and a 2x squared. Well, that is 2x squared times 2. So now I can say that 2x squared equals 2x squared times 2 is 4x squared. This is a parentheses, not a 12. That looked like 12 for a minute. Okay, so this is 2x quantity squared. And I can factor this out and say, well, 4x is 2x quantity squared. Because if I distribute that, I get 4x. And if I distribute that, I get x squared. So what did I do there? I just factored out. I factored 4x. Factored out a 2 and an x, and it's 2x quantity squared. And we just proved that this is true. And therefore, since 2x quantity squared equals x squared plus 1 squared minus x squared minus 1 squared, we have shown that x squared minus 1 squared plus 2x squared equals x squared plus 1 quantity squared. And thus the numbers x squared minus 1, 2x, and x squared plus 1 form a Pythagorean triple. Then by the converse of the Pythagorean theorem, a triangle with these 3 side lengths for some x greater than 1 is a right triangle. Woo-wee. Okay, page 2, example 2. Next, we describe an easy way to find Pythagorean triples using the expression from example 1. Look at the multiplication table below for 1 through 9, for 1, 2, ... all the way out to 9. Notice that the square number 14981 lie on the diagonal. 1491625 all the way out to 81 lie on the diagonal of this table. What value of x is used to generate the Pythagorean triple 15, 8, 17 by the formula that we just derived on the last page? How do the numbers 1, 4, 4, 16 at the corners of the shaded square in the table relate to the values 15, 8, and 17? Okay, so first of all, if I want to, it says what value of x is used to generate the Pythagorean triple right here by this formula? Well, we would take x squared minus 1 and set it equal to 15. Our first term has to equal our first term. So if I say x squared minus 1 equals 15, and I add 1 to both sides, I get x squared equals 16. And if I take the square root of both sides, I get x equals plus or minus 4, but distance can't be negative, so we're just going to use the principal root, x equals 4. Then if I move this and focus on, let's get that over a little bit, focus on the 8, that came from 2x. So if I say 2x equals 8 and divide both sides by 2, then I get x equals 4. Okay. And then if I take the 17 and the x squared plus 1, then I say x squared plus 1 equals 17, and I subtract 1 from both sides, then I get x squared equals 16 again. And when I take the square root of those, I get x equals the principal root 4. So obviously x is the same for all of these. So it says what value of x is used to generate the Pythagorean triple? Well, it was x equals 4. So if we used a 4 by 4 square on our multiplication table where the diagonals are our perfect squares, where do these numbers come into play to determine our Pythagorean triple of 15, 8, and 17? And it's actually pretty mind-blowing. 4 plus 4 is 8. 16 minus 1 is 15. And 16 plus 1 is 17. Whoa. So this plus this plus that, and this minus that will give us our Pythagorean triple. Mind equals blown. B, now you try one. From a square on the multiplication table below, whose left top corner is 1, as in the example above, and whose bottom right corner is a square number, use the sum or differences of the numbers at the vertices of your square to form a Pythagorean triple, and check that the triple you generate is a Pythagorean triple. Okay, so I'm going to do this now. I'm obviously probably not going to pick the same one. I might, but if you did this already, then I'm going to go out to 64. So I'm going to, what in the world? Let's try that again. Pick this. I want my line color to be purple, and I want my fill color to be nothing. And I'm going to go out to 64. That's better. So there is our square. And what I want to focus on is, let me highlight this. I'm focusing on the 1, the 64, the 8, and the 8. So there are my corners. All right. So what did we do here? Go back to my pen. 64, well, 8 plus 8 is 16. So I got 16. 64 minus 1 is 63. 64 plus 1 is 65. This should be a Pythagorean triple. Longest side being 65, if I write a squared plus b squared equals c squared, then I get 16 squared, and I usually make a the smallest number just so they're in order from least to greatest. 16 squared plus 63 squared has to equal 65 squared. So let me get my calculator out because those are pretty big numbers. All right, and let's see, 16 squared is 256. plus 63 squared is 3,969. And 65 squared is 4,225. Now 9 and 6 is 15, carry the 1. 6 and 5 is 11, plus 1 is 12, carry the 1. 9 and 2 is 11, plus 1 is 12, carry the 1. And I get 4225 equals 4225. That makes the Pythagorean theorem true, and therefore our 16, 63, 65 is a Pythagorean triple. Oh, that's pretty cool. All right, page 3. Let's generalize this square to any square in the multiplication table where two opposite vertices of the square are square numbers. All right, so we can move this anywhere. We can make it any dimension, but our top left, bottom right have to be perfect squares. So let me just highlight that for starters. Okay, in order to do this, this number and this number have to be perfect squares. Okay. Okay, so how can you use the sums or differences of the numbers at the vertices of the shaded square to get a triple? Well, in this case, these are 15, so 15 plus 15 is 30. 25 minus 9 is 16, and 25 plus 9 is 34. So if I check this now, 16 squared plus 30 squared should equal 34 squared. So if I get my calculator, let's just do it all at once now. 16 squared plus 30 squared, enter. 34 squared, enter. And lo and behold, that's the answer. So how can you use this sum or differences? So what did we do? Add the top right, bottom left corner. That gives us the middle term. Take this minus this, which is this part here is 25 minus 9, comma, 15 plus 15, comma, 25 plus 9. All right, so you add the two that are equal, and you add and subtract the other two, and that gives you the three numbers. And yes, this is a Pythagorean triple. So now it says using x instead of 5 and y. Okay, and by the way, our x was 5. I haven't discussed this yet. Our x was 5 for this square. So using that Pythagorean triple, x squared minus 1, 2x, x squared plus 1. If I put 5 in here, 5 squared is 25 minus 1 is 24. 5 times 2 is 10. 5 squared is 25 plus 1 is 26. That would be if we went all the way out here and 25 minus 1 is 24, 25 plus 1 is 26, and 5 plus 5 is 10. So this works only when we're using the squares that go all the way to 1, just to keep that straight. It doesn't work when you pick a value with a square inside like this where the top left is not 1. All right, so let's move on to D now. Using x instead of 5 and y, instead of 3 in your calculator in part C. Okay, so let's go back to C. Write down a formula for generating the Pythagorean triples in terms of x and y. Okay, so I put some highlights up here. 5 squared is 25, 3 squared is 9. So now it says using x instead of 5. So instead of putting a 5 here, we're going to use x, and y instead of 3. So this is y, and this is our y, and this is our x. That's what they're saying. In your calculations in part C, write down a formula generating the Pythagorean theorem triples in terms of x and y. Well, if I look at 25 minus 9, that would be x squared minus y squared. So that'd be x squared minus y squared. Okay. How did I get this? 15 plus 15. It's x times y. So it's xy plus xy, right? X times y, 5 times 3, 15. And then 25 plus 9, well, that is going to be x squared plus y squared. All righty, so there it is. So here we have it. The calculation 25 minus 9 generalizes to x squared minus y squared as the length of one leg. The length of the other leg can be found by 15 plus 15, which is 2 times 3 times 5, which we could generalize by 2xy. Well, xy plus xy is 2xy, all right? And then the length of the hypotenuse, 25 plus 9, can be generalized as x squared plus y squared. So it seems that Pythagorean triples can be generated by triples x squared minus y squared times, comma, 2xy, comma, x squared plus y squared, where x and y, x has to be greater than y, and y has to be greater than 0. Okay? It's pretty impressive, actually. So here's some relevant facts and vocabulary. I will leave that to you. Okay, page 4 brings us to the end of lesson 10. Go to your problem set.